So I said earlier that we want to be a little careful about some of the theorems that we proved when they have existential quantifiers, because we want to make the theorems that we prove as useful as possible. So I'd like to show you more really what I meant by that. So consider this theorem. For all x squared is always greater than or equal to 0. This is a true theorem, right? And here's another one. For all x is greater than or equal to 0 implies that there exists a y such that y squared is equal to x. Okay, so yeah, these are both true theorems, and you can use them in proofs, of course. I want you to consider some other theorems that we could have. For all x, actually let me erase that. There exists a y such that for all x squared is greater than or equal to y. Okay, this is another true theorem, right? And it's true because, in fact, well, y could be 0, and then it's exactly for all x, y squared equals 0. Here's another one. For all x is greater than or equal to 0 implies that the square root of x squared is equal to x. Okay, so let's consider the theorems that we have. The first row has two theorems that actually say the same thing. However, I'm going to say that this one here is a strong theorem, and this one is actually weak. Okay, and the reason that it's weak is that it tells us that there is some number that is smaller than x squared, but it doesn't tell us which number, right? The strong version actually tells us what the number is. Likewise, in here, this theorem is strong, whereas this one is weak. Okay, and again, the strong version of the theorem tells us not just that there exists a y that has this property, it actually tells us what a y is. It's the square root of x, right? So the strong versions in many ways are preferable. Okay, and the reason that they're preferable is that when I'm using those in a proof, I don't just get the fact that there exists some number with this property, I actually get to know what that number is, right? So that's a lot better for many cases, right? Now, that's not a complete out and out, always follow this rule kind of ideas. There are some very important theorems that actually we prefer to say there exists an x with this property, simply because there's no easy way to find it. So really we don't care, So for example, here's a simple theorem. Suppose that you go from 0 to 1, and you come from 1 to 0, right? No matter how you do it, well, there's one place where those two will meet. And you can see that that's something that has to be true. We don't actually care where they meet. It's good enough just to know that they have to meet someplace. And actually, in general, you wouldn't be able to find that point very easily, right? So it's actually convenient to just be able to say, and they meet somewhere. Okay. So anyway, but if you can, then it's better to actually put the correct answer in the theorem as opposed to having an existential.